Okay, new stuff. 6765 Mechanical Behavior Materials. Today we're looking at deformation of non-crystalline and semi-crystalline materials, meaning glasses and polymers. Plastic deformation in particular. Right? We've already talked about elastic deformation in these materials. So we're going to start today by looking at the structure of non-crystalline solids and the notion of viscosity. That'll be the first part. The second part of the lecture will be on inorganic glasses and metallic glasses and deformation in these. And the last part will be on plastic deformation of polymer structures. Okay, so let's jump right into it. So, non-crystalline materials show no long-range order. Right? So here we have a amorphous metallic structure versus a crystalline metallic structure. What's important to recognize about these are this picture is a little misleading, and the discussion in Courtney is a little misleading because in a metallic glass, the local structure is extremely close to the crystalline counterpart. Right? So each atom has the same number of neighbors, and the bond angles are approximately the same. So a lot of metallic glasses are based on BCC materials, and the neighborhood around each atom is very close to BCC. It's just when you deviate away, when you go far away, and you look at the spatial relationships on a longer scale, they don't um, match up very well, right? So you have amorphous, no long range order, but locally your structure looks a lot like it does in the crystal part. So just keep that in mind. Okay. So in all materials, right, if we're above the melting temperature, right, the non-crystalline arrangement is thermodynamically stable, right? Liquids don't have any long-range order to them. But on cooling, all metals, virtually all metals, will adopt a crystalline conformation below the melting temperature. However, if we cool it fast enough, the mobility of the individual atoms can decrease faster than the driving force for crystallization, right? So you essentially can lock in an amorphous structure. We'll talk more about that later. Soda glass, or silicate glasses, of which soda glass is one. This is just pure SiO2. The main component of the silicate glass is it's very difficult to crystallize even when cooled very, very slowly. So you get these tetrahedra of oxygen and silicon uh, tetrahedron. And so you have this kind of amorphous structure. And if you want to crystallize, you have to break and reform a lot of silicon oxygen covalent bonds, right? Which is very difficult to do at temperatures below, significantly below the melting point, right? So metals crystallize very easy. Glasses, inorganic glasses, on the other hand, tend to crystallize very, very slowly. Okay. So if we can cool a material fast enough, the non-crystalline crystalline transition can be suppressed, right? So So here we have the volume versus temperature, right? So when we're cooling, oh, okay. So up here, the liquid, right? Once we hit the melting point and crystallization happens in metals, right? You have a discontinuity in your temperature volume curve, right? The volume of the liquid is not the same as the volume of your crystal. So you have a discontinuity here, right? Remember your thermodynamics, right? And the types of phase transformations that are possible. Now, the amorphous solid, on the other hand, right, isn't going to have this volumetric change because it's not crystallizing. It's not undergoing a phase transformation, right? So you get a continuous change through the melting point, right? So on further cooling, now we approach the glass transition temperature, right? And the material begins to gain rigidity, and there's also a change in the thermal expansion coefficient at the glass transition temperature, right? So if we're below this glass transition temperature, the material is going to behave like a rigid solid or a linear elastic solid. Above, it's going to act as a viscous material between the glass transition temperature and the melting, and above the melting temperature, it's going to act like a liquid. Okay? Now, even though we're below the glass transition temperature, if the bond strength is weak enough, like in metals or polymers, we can still exhibit some measurable plasticity here. But if it's covalently bonded or ionic, well, ionic you don't get amorphous ionic solids. At least I'm not aware of any. Someone will prove me wrong. But covalent, you're not going to have the energy to break the bond is going to be significantly higher than the fracture. So you're not going to get any plasticity there. Okay. So the glass transition temperature is not a intrinsic material property, right? It also depends on the processing. It depends on how fast you cool it. Right? If you cool it slowly, you end up typically with a lower glass transition temperature than if you cool it quickly, and your specific volume also ends up being a function of the cooling rate. So if you cool something quickly, cool a glass quickly, amorphous material quickly versus slow, you have a higher specific volume. So what does that imply? Right? It means that there is some amount of volume that is trapped in your material that is an indicator of the material state. Right? We call this the free volume. Right? And it's a very important concept. Right? Free volume is how I tend to think about everything with glasses or polymers. Right? It is it's kind of like an order parameter, right? It's a way of describing how far the current local atomic structure deviates from a reference or an ideal atomic structure, right? So some authors define that reference or ideal state as the crystalline molar volume. or crystalline specific volume. Uh, Other authors say an ideal amorphous, which is more broadly useful, but it's harder to define. What do you mean by the ideal amorphous structure? Um, but you can just think of free volume as a local volume difference um, between some reference state and the current amorphous state, right? And it quantifies how much extra space there is other than what you need to pack your atoms, right? That is available for the displacive flow of atoms or molecules, right? The higher the free volume, the easier the plastic flow. You can imagine um, a bunch of hard spheres, right? If I just dump a bag of marbles into a big beaker, they're not going to be perfectly packed. There's going to be large regions where the marbles aren't touching. But if I put that on a shaker and gently shake it for a couple days, or I start by shaking it uh, and I slowly lower the amplitude of that shaking over a couple days, I'm going to have my marbles are going to be more closely packed together. I'm going to be reducing the amount of free volume that the individual marbles have. And there'll be a lot less at the end of that. There'll be a lot less room for them to vibrate around. It'll be a more difficult to get them to slip past each other. So empirically, we have this kind of a viscous flow law. So for elasticity, our stress was linearly proportional to our strain, right? That's linear elasticity. For a viscous material, our stress is proportional to our strain rate, right? Or our shear rate, right? So eta is our viscosity, right? If the material is Newtonian, right, eta here is independent of the applied stress, right? So if it's non-Newtonian, this is going to be a function of stress itself, right? And our local viscosity and our local flow depends on the free volume, right? So basically, right, we can just think about this in terms of an activation energy threshold, right? And if there's less free volume, right, this difference between an energy between the initial state and the final state, right, is basically our stress times the activation volume, right? So the difference in this energy tells us something about the number of atoms that have to be involved, or the number of molecules that have to be involved in getting out of each other's way for the deformation to occur, right? So here we see a region of a local pocket of free volume, and under a shear force, atom A can jump from this position to this position, right? And these displacements are going to occur in regions where the free volume is higher, right? We've got activation energy that we have to overcome. So it's not likely to happen just by thermal fluctuations, but by applying a shear, a stress, we give the system more energy, right, to assist this local hopping, right? And the number of coordinated atoms that need to, the coordinated motion of the atoms, right? We can get some information on that from the change in energy from before or after the jump. Right? So that's kind of the main ideas there. Okay, sorry for the jump cut there. So there's several different viscosity models that can be used to develop a physical picture of what's happening. What I talked about in the previous slide is related to the reaction rate viscosity model, where we assume that we have stress-associated motion of atoms, right, that have to overcome an energy barrier for the jump to occur, right? And the stress is going to bias the atomic motion in one direction over the other direction, right? It's effectively, the stress is reducing the activation energy, the activation barrier to make the jump, or effectively reducing the activation energy to make the jump. So the energy decrease is going to be given by the force times the jump distance, and we can substitute the shear stress times the area for the force, right? A here is the effective area on the plane of shear, right, which is equivalent to a slip plane or a pseudo slip plane in the area in the glass, and we can further make the substitution that area times the jump distance is going to be the activation volume, right? So the net rate, right, the number of atoms per second moving in the bias direction, right? If we consider the calculating the rates of the atoms jumping to the right and the left, so we have an unbiased and a biased term, the difference between them, right? That gives us our net flux, and this is just a simple Arrhenius relationship. Here nu is the atomic vibration frequency, right? Or the number, this is the number of possible jump attempts, right? How many times the atoms vibrate back and forth in a given second, right? And then this encodes the probability of a successful jump in the positive direction. Okay? So the shear rate is going to be obtained by multiplying the flux, the number of jumps per second, by the jump distance. Right? So this is equivalent to basically the Orawan equation, right? The velocity of the dislocation times the Burger's vector length, right? So here we've got the flux, the number of jumps per second, which is essentially a velocity term, and the jump distance, which is equivalent to the Burger's vector, all right, divided by the vertical spacing between the atoms. Now, if we assume that our structure is isotropic, the jump distance is going to be the same as the separation in the orthogonal direction. So that means our shear rate is going to be approximately equal to our flux. Right. So now how do we get to viscosity? Well, if we remember back here, viscosity is can be our shear stress divided by our shear rate. So if we do that, we have an expression for viscosity that looks like this. And if our stresses are pretty small and our temperatures are pretty high, right, this term here is going to be much less than 1. And so we can make our approximation for our high temperature viscosity like this, where our viscosity becomes independent of the stress. So this is basically our Newtonian assumption, right? That our stresses are small and our temperatures are high. Excuse me. So our viscosity becomes independent of the stress. Right? As we lower the temperature, the viscosity is an explicit function of the applied stress. And this theory is going to break down as we get close to the glass transition temperature. Right? So the applicability of this model is between the melt temperature and the, well, it's still valid above the melt temperature, but above the glass transition temperature and higher. Right? And it's also going to depend on the stress. Right? For very high stresses, this is going to break down. Okay. So the reaction rate viscosity is kind of thermodynamic in flavor. We think about things in terms of an Arrhenius rate type behavior. The free volume has a little more structurally. It still comes down to the Arrhenius model is a probability model, basically, right? How likely is a jump to be successful, right? It depends on an exponential probability curve. Here we also have a probability curve, but instead of, we just think about it in slightly different way, right? So as we said before, viscous flow depends on the probability of finding a large open volume near the atom that's going to make a jump, right? And the probability is going to depend on the free volume, the average free volume, right? So if we think of the shear rate as the probability of having enough free volume locally to accommodate the jump times the stress, right? We can develop a viscosity term that looks something like this, right? This is the ideal or reference free volume, depending on whether you're talking about a crystalline reference or an ideal amorphous reference. This is the actual, right? And the temperature dependence is introduced by considering the differential thermal expansion between the amorphous and the crystalline states, or the amorphous and the ideal amorphous reference state. So we can consider that in the temperature change is going to alter your local free volume concentration because of this differential thermal expansion. And so we have a free volume viscosity that looks like this. Right? It's a more conceptual model than the reaction rate viscosity. And so here we have 1 over T times 1,000. Right? So the units of this is Kelvin, 10 to the 3 Kelvin inverse. Right? And so what you can see is that for these two organic compounds, right, it's good when the temperature is high, but as the temperature approaches the glass transition, we still break down. Okay? And so this free volume, it really predicts a Newtonian-like behavior. Right? So good for inorganic glasses and metallic glasses, again at high temperatures and low stresses, it's a really poor assumption for polymers. Right? Polymers almost never behave in the Newtonian regime. So, because of the long structure. But those are the two basic models for viscoelasticity. I mean, for not viscoelasticity, for viscosity, and pretty much they're good models to keep in your head for trying to rationalize what is happening. Right, and there's a lot of things we didn't talk about there, such as free volume generation, right, and free volume annihilation and relaxation, and free volume diffusion, right? But these are kind of second order or higher order effects, right? That when you're thinking about initial flow behavior, don't really come too much into play. We'll talk about that. We'll talk about some of these ideas a little bit more when we get into the metallic glasses. So, okay, up next is deformation in inorganic glasses and metallic glasses.